Good morning, Fancy Meat Computers. How's everybody doing today? Hope you're all doing okay. I might be a little on the quiet side today, just because I am not feeling very well. I wasn't faking. I didn't just want to spend the rest of the week at home. I'm actually not feeling great. Also, I think I have a blocked tear duct somehow. That's just terrible. So how is everybody today? Oh, we've got some people coming in now. Good. Not too bad. Sadly, calc midterm tonight. Oof. Gross. Tired. Yeah, I hear that. I have my convocation tomorrow morning. I'm going to be actually getting the piece of paper that I've worked for so many years to get. So that's going to be fun. Although I hope I'm feeling better by tomorrow. So, might as well get into it then. So I'd just like to summarize why we would use linked lists over arrays. I went over it a little bit. Thank you. I went over it a little bit last time, but it bears repeating because it's important to understand the trade-offs between linked lists and arrays, because if you understand the trade-offs, then you have to understand what's different about them and why they're used in different situations, which is very important. So linked list versus arrays, why go to all the bother? It seems like a lot of work just to make something that functions roughly like an array anyway. Linked lists are not stored in contiguous memory. 6. I can draw on the slides. They are not stored in contiguous memory. For those of you who do not remember the meaning of the word contiguous from your high school geometry classes, it means that they are continuous with no gaps in between. Contiguous shapes must directly abut each other. It can be dynamically or grown or shrunk without having to copy the whole array. Because the next node is indicated with pointers and the pointers may be modified, we can insert an element without having to move any other elements in memory. Now, hopefully, you guys have performed this type of operation successfully on an assignment before. But if, let's just say for the sake of interest, we had a region of memory that looked like this, right? And let's say, well, actually, let's make it look like this. Let's say we wanted to insert the 2 at the appropriate place. 1 remains the same. What we then have to do is we have to find some additional place for 6, put that there, copy 5 to 6's location, copy 4 to 5's location, copy 3 to 4's location, and then insert 2 at the correct point. So inserting something any particular point into an array is actually a linear time operation. It takes at most the number of elements of the array's worth of time to be able to process that. So good. Because the next node is indicated with pointers, these pointers may be modified in constant time, and we can insert an element without having to move any of the other elements in memory. However, there are some drawbacks. Because nodes are not stored in continuous memory, we can't perform pointer arithmetic to find a particular index. Instead, we have to follow the node pointers or walk the data structure. Thank you for the congratulations. This means that finding the record at index I takes I operations, where an array can do it in one operation, or proportional to one operation anyway. So now we talk about doubly linked lists. Doubly linked lists are essentially the same idea as a singly linked list. It's just that you have these backlinks through the data structure indicating the previous node, or the node which is pointing to this node through the the forward pointer, the next pointers. The previous pointers are all embedded inside of the node struct as well. So now we have more pointers to worry about, but we gain a very crucial ability here. We gain the ability to move backwards through an array without having to trace the whole thing out again from the beginning. And this can be very useful depending on what your application is. With the addition of one more pointer previous, we have made a singly linked list node into a doubly linked list node. Ta-da! This is the new one. The first element's previous pointer will point to null in the same way that the last element's next pointer points to null. While a doubly linked list increases the amount of bookkeeping, it makes the list traversable in either direction, which might be very important depending on your application. If we were to visualize this, you would see it as follows. You see that each one of these structures now has a next pointer and a previous pointer, and these pointers are just pointing to the next and previous nodes, as you might imagine. Good. Are there any questions about doubly linked lists before we move on? Give me a thumbs up in the chat if everything's making sense to you. Are SLL node and DLL node types/keywords similar to int and char? They are similar to int and char insofar as you can use them in your code no matter where. Like, if you've defined the structure, then you can use SLL node inside your code wherever you might use a data type, right? However, they are not provided by they are not provided by C. They don't exist in any C library that I'm aware of. And yeah, so it's not like you can import these from the standard library. But yes, once they've been established, you can use them in the same way that you use any other data structure. Or data type, pardon me. So to access a certain value in the list, you need a for loop. Well, remember that for loops are just syntactic sugar for while loops in C. But yes, to access a particular, like if you wanted to access the fourth element here, you have this node's address. So you loop through, follow, 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 and then you stop. Normally you keep track of an index that decrements every time you step one node over, so that when it reaches 0, that's the stopping condition. Pardon me. That's the stopping condition for your loop. There we go. So, we're now going to talk about binary trees. It's a Christmas tree with a heap of presents underneath. Harf, harf. It's a joke. That's actually a binary. Well, no, it's not quite a binary heap. Pardon me. Cool. So, not to make things more complicated, but let's make things more complicated. One of the very, very useful data structures that you'll find when you study data structures next semester is the tree. Binary trees are extremely, commonly used. We get a little bit into one of the applications of them a little later on. But let's just go over the structure. A binary tree is an acyclic directed graph where each node may be connected to at most 2 others. Trees have a root node, here R. The root of a tree is the node to which no other node points. Or, depending on which way you want to put the arrows, it can be the node which points to nothing, or points only to itself. The selection of having the arrows go up or down is somewhat arbitrary. You can structure the tree either way. If you have the arrows pointing down, that means that each node keeps track of its 2 child nodes, right? But if you structure it the other way, each child node keeps track of its 1 parent, but that interferes somewhat with your ability to walk the array, to walk the tree. So this is the preferred configuration for now. For every vertex v, there is exactly 1 path to that vertex from the root node. So it doesn't matter which one you pick, there's always only 1 path to root from that node. Each node has exactly 1 parent, except for root, which has no parents, and up to 2 children. Binary trees have at most 2 children. N-ary trees have at most n children. And some trees you don't even restrict how many child nodes you can have. Good. A leaf node is any node in the tree which does not point to any other nodes. So all of these are leaf nodes. Another way of thinking of it is that a leaf node always occurs at the end of a path from root. A stem node is any node in the tree which does not point to other nodes, which does point to other nodes, pardon me. So everything in the middle, including root, is considered a stem node. The depth of the tree is the number of nodes in the longest branch. That is, the distance from the root to the furthest leaf nodes. So in this case, all of our leaf nodes are the same distance from root, but you can imagine a tree in which that was not the case, such as this one. 1, 2, like 1, 2, 3, 4, 1, 2, 3, 4, 5, right? The depth of the tree overall, in this case, would be 5. Good. The nodes of a tree are organized into levels. All nodes of the same distance to the root node are at the same level. The width of a level is the number of nodes in that level. A set of n greater than 0 disjoint trees is called a forest, as we stated previously in class. So, how would we go about implementing such a thing? Whereas the singly linked list had only one next pointer, the binary tree has 2. By convention, we call these left and right. Left, right. One interesting property of trees is that they are a naturally inductive data structure. Linked lists, I would argue, also are a naturally inductive data structure. Both the nodes pointed to by right and left can be rightly considered the roots of their own subtrees. Therefore, this is a natural application for recursive algorithms. If you remember way, way back when we talked about recursion, I said there are some types of problems that lend themselves more easily to a recursive solution, than an iterative solution. In general, things that have to do with naturally inductive data structures, such as binary trees, that's like your primary candidate for recursive algorithms. So, good. Any question about that before we get on to the next slide, which is about summing the nodes in a tree? Give me a thumbs up if you're following along. There we go. Thank you, Andrew. So let's take a tree and let's talk about an algorithm that might recursively sum all of the values in the tree. Yeah. So in terms of an inductive, or in terms of an inductive definition, we might say that the sum of any particular tree is the sum of the left tree, the right tree, and added to the value of the root node. So if we have some trees, if I have a root node, right, it's the sum of everything on this branch plus the sum of everything on this branch plus this guy as well, right? So here's our algorithm. If the left tree doesn't exist, like it has a null pointer or something like that, points to null, its sum is 0. If the left tree does exist, we recursively call the summing function on the left tree, considering the node pointed to by the left arrow to be the new node in this recursive call. We hold on to the value to return later to the calling function. We repeat steps 2 and 3 with the right tree, or 1 and 2, I think that should be. We add the results of steps 1 and 2 to the value of the root node and return this value. So let's see it in action. So let's imagine we had this tree, right? A left tree exists. Okay, so we head down that way. A left tree exists, so we head down this way. There's nothing left to sum here, so 81 is returned to the calling instance. We then head down the right path. There's nothing left to be done here, so we return 66. We compute the sum, which is not 95. Why does it say 95? It's very strange. That's 154 right there. So, having found the answer to this left branch of the tree, we then head down the right branch, examining 29, which has a child. So we find that child, bring it back up, bring it back up. That does look to be correct. So in the end, we can find a final value for the sum of everything in the tree. 1996, which is 269. There we go. So in this example, we're sort of doing a silly thing, which is to overwrite the values in the nodes. This is mostly for the demonstration purposes. A real algorithm wouldn't overwrite node contents like this. Wouldn't it be 155? Let me see. Did I do my math wrong? Yeah, it would. Yeah, okay. All right, add 1 to this and add 1 to that. So it's 270. That'll be fine. Thank you. So, what we just saw was an example of a very fundamental graph searching algorithm. It doesn't just apply to trees, but it does certainly apply to trees. We saw an example of depth-first search. Depth-first search selects a branch and follows it down until a leaf node is found. If a leaf node is reached without the searched for item being found, depth-first search backtracks to the last node where it made a branch decision and tries another branch. Depth-first searches can be suitable for exploring decision branches in game AI. And then we have breadth-first search. Breadth-first search searches all nodes in one level of the tree before moving on to the next level. It requires more traversal or bookkeeping than depth-first search, and it finds the minimum branch depth faster than depth-first search. Breadth-first search is also often used to find the shortest path through a graph. It just so happens that I'm actually teaching this almost the same material to my algorithms course, my algorithms class at this point in time, and so it might be like interesting for you to see what this looks like in an algorithms course. But obviously slides from another course are not like testable or whatever, but this is mainly just in case you're interested. So in depth first search, if you have like something that's not a tree, right, you can see that in these diagrams we're sort of, the red arrows are the things that are searching. So we search, search, search. There we go. And depth first searches actually can be used to turn a general graph into a tree. The breadth first search, the way that it does this is it actually maintains a queue where if you examine one node, you put all of its children into the queue, and then you examine each of those in turn, adding more nodes to the end of the queue as you go. That's how breadth first, the bookkeeping in breadth first search works. Depth first search versus breadth first search is a popular topic among people who think computer algorithms have application to human behavior. One particular area that I've heard this depth first search versus breadth first search as applied to human behavior was in the process of dating or trying to find a life partner, as it were. The person who was saying this says that you want to go for breadth first search rather than depth first search in order to find a possible mate, so that you are testing the available field before you get too deeply involved with any one person. I thought that was a very, that was a very sexual revolution type approach to the problem. It's I don't think it's as simple as all that. For one thing, human beings aren't trees. I don't think that the structure really maps that well. But if there's one thing that people love doing, it's trying to take all of the rich complexities of human life and imagine it's as simple as the toys we play with. By which I'm including computers. If I was feeling a little less crappy, I would be like inclined to say something like, good dating strategy is to just be yourself and don't be a Seinfeld episode. But I don't know, it's kind of like, it seems like a lot of people like took Seinfeld as being like, a mode of behavior which is acceptable, but really like Seinfeld is spoofing it. And like Seinfeld is an interesting show because it understands that all of the characters in it are terrible people that are just trying to justify their terribleness. Like, and that's kind of like the conclusion of the show too, is like, in the final episode where they're all brought up on trial for violating the Good Samaritan laws, it's like, oh, these were bad people the whole time. Yeah, they don't really have redeeming qualities. Anyway, so you might ask yourself, okay, sure, trees sound useful, but are they? And the answer is yes, trees are very useful. One thing that you can use trees to do is to accelerate searching. So both depth-first search and breadth-first search assume nothing about the structure of the data contained in the trees, aside from the fact it is a tree. Steins Gate the anime? I don't know what that means. If we give trees certain mathematical properties, we can write algorithms that vastly improve general case runtimes. So, it's a big issue trying to organize data in a manner in which you can find the data quickly and easily when you need to. A very basic approach to improving searching algorithms is the binary search tree. So, the binary search tree property is as follows. If a node has a left child, the value of that node is less than or equal to the value of the parent node. If the node has a right child, the value of that node is greater than the parent node. It doesn't really matter which side the equal sign is on. It could be on both, in fact. Depending on who writes the algorithm, duplicate elements are sometimes disallowed. So, again, I'm going to just show you some slides from the other course, just because it might be of interest to you. So, binary trees, right? The way that they work is you know what key you're looking for. You can make a judgment about which path to follow based on the value of the current node, right? So if we're looking for H in this example, we know it's less than S, we know it's greater than E, less than R. There we go, we find it. We put new values into the tree via a very similar process. So normally, if you add a bunch of random numbers to a tree in this manner, you end up with a runtime that is around logarithmic time, which is very, very good. We haven't really talked about logarithmic algorithms yet, but we've talked a lot about linear algorithms. We've talked about constant algorithms, but a logarithmic algorithm takes well, it takes a logarithmic amount of time to execute. So, for example, if you had the log base 2 of 1 billion is about 30. So if your binary search tree is perfectly constructed, then the amount of time it takes to process 1 billion elements is 30 steps, which is, extremely good. These types of logarithmic time algorithms are the only reason that big data applications work, like in a very real sense. If it weren't for logarithmic time algorithms, nothing would work. Nothing would work. We'd still be in the 80s. Even in the 80s, they had these good algorithms. So many of these algorithms were developed in the 1960s. So the best case scenario is a tree of depth log base 2n, where n is the number of nodes. That's sort of a perfect tree. A worst case scenario tree. This is the best case scenario, right? This is what you kind of get typically. The worst case is everything lines up all in a line like this, which can happen. the structure of the binary search tree depends on the order in which the nodes are added. But if this is what you're looking at, this is no better than a linked list, right? So in the worst case scenario, the worst case is actually the depth being n, pardon me, which means that your worst case runtime is linear. If the search tree property is maintained, also another con is that you need to maintain the search tree property, which requires some extra bookkeeping, but generally this is fine. To address the drawbacks of unbalanced trees, binary search trees in practice often use balancing algorithms, such as red-black trees, or Adelson-Velsky and Landis trees, or 2-3 trees, or B trees. Again, this is exactly the kind of stuff that I was covering in this other course I'm teaching that's dealing more exactly with this type of thing. But you can do various things with these trees. You can include more than one value in the node and only expand it from the root so that it expands evenly. This makes sure that you're always a set distance from, like, all of the branches are always maintained completely evenly. You have red-black trees, which are like a variant on that doesn't like the idea of storing multiple nodes, multiple values in a node. But yeah, so any questions about that? Give me a thumbs up if you're doing good. I tried making fortune cookies once. It didn't go very well. They ended up very greasy. Could I reiterate the difference between red-black trees or Adelson-Velsky Landis trees? No, it's not worth going over, to be honest. It's well outside the scope of the course. But if you're interested, just for the sake of interest, like the problem, right? The problem with these with binary search trees is that you might get them all lining up and have a very long path length through the data structure. Me too, but mine's bird hands trying to fold them while hot. Ouch. Ouch. So basically, like, it's a little bit complicated, but red-black trees, like, there's a specific manner in which, like, these red links have to be managed. Like, they always have to lean to the left, and no two red links can be adjacent, or else you have to reconfigure the tree. But essentially what the red-black tree does is it establishes and maintains a property where the tree is black balanced. So if you consider any any path through the tree, it's always going to have the same number of black links as every other branch through the tree. So it's like a quote-unquote balanced tree. In practice, it's like not quite balanced, but in practice, it maintains itself. It gives itself enough balance as to remove the possibility of everything lining up in a line. So it addresses the worst case scenario runtime of the binary search tree without introducing too much complication. Red-black trees are actually brilliant, in my opinion. So there you go. For a doubly linked list, how do you go about storing the previous pointer? Do you store it in a variable before moving on to the next node? You don't need to. This is the wrong set of slides. In a doubly linked list, you don't need to store the previous... you don't need to store... Like, if you're walking the array, you don't have to worry about storing previous values unless there's, like, some point of importance about them other than just the fact they exist. Because you have the previous node baked right in, or the previous pointer baked right into the node, you can just follow it back and forth however you wish. So no, you don't. It eliminates the need for storing that auxiliary information. This is like a replacement for that process. Good. All right. Discard changes. I'm feeling feisty today. That's not true. I'm feeling the opposite of feisty today. So, moving swiftly on. We're going to talk about now, basically, we're almost done C programming. With respect to this course, after this topic, the rest of the topics are not about C programming. C is a kind of a small language, and I feel that we have done it justice in the 9 topics which we've covered. So really, we just have a few more like miscellaneous items to clean up, and then we will be talking about other things. You will be expert C programmers. So the things that we have to clean up, we have to talk a little bit about preprocessor stuff, how to take input from command line, and then we'll talk about signals, which is slightly like exception handling in C, but C doesn't have exception handling. I mean, how do you know what the previous node is in order for you to assign it to the next node? Oh, yeah, okay. So, if you have, let's say you have, good. So let's say, just for the sake of argument, we have a very simple doubly linked list. Yeah? So, let's say we wanted to insert a node, right? Here. We want to insert this one between these two. You would have to, do I have an eraser in this bank of crazy things? I think I do. Ooh, oh wow, that erases everything. Wow, okay. This erases everything, okay. What's this do? That's interesting. Alright, never mind. Stop playing. So you take this pointer here, right? And you redirect it. I'm actually just going to continue to use the pen. You... Oh my god. Stop. There we go. All right. You So you take this guy, right? You redirect him to point to this guy. Then you take this guy, you redirect him to point to this guy as well, right? Then you make symmetric operations here, right? And then that inserts him into the list. So where did we find the previous node? Well, during the insertion operation, we would have had a pointer pointing to this guy. We would have had a pointer pointing to this guy, or just directly referencing them, using address of and the rest of it. And then you just take those values and you put them where they should be, and that's how it works. You also need one here. Does that make sense? Hopefully that makes sense. So, let's talk about preprocessor directives. So, what's left? Not much. We need to go over some of the advanced processor commands, preprocessor commands. We'll talk about define, undef, if and if, error, pragma, and line. The C preprocessor is responsible for handling all of the operations that need to occur before a source file can be tokenized, an abstract syntax tree produced, and an executable generated. Comments must be removed. Preprocessor directives must be processed. A preprocessor directive is some manipulation of the text of the source file. We have seen define statements before. This is macro man reprisal. At the beginning of the course, we explained how macros can set symbolic constants, but we can do much more with them than just specifying the size of an array. Remember that a macro is character substitution. This means that a macro can be used to insert anything into a C file, including semicolons, curly braces, complete or partial expressions, arguments, assignments, argument lists, and function calls. Macros have no grammatical limitations, though the substitutions they make must result in grammatically correct C code. It is recommended to keep these substitutions to one line. Macros are named in all caps by convention. For example, we define begin as round braces open curly brace. Twice x is xx. Int print substitutes, inserts x into printf, our familiar printf statement for printing integers. And area, xy, takes x times y, and it inserts x times y. So, a correct program then, int main begin, so begin inserts that. If 1 equals 1, int print area 8, 10, and then twice the close curly brace. So very quickly, I'm going to show you how how C makes these substitutions. Oh boy. So, it'll generally go in order that the macros appear. So, begin will be substituted with this. Int print will be substituted for printf d, comma, and then x is this, so x will be substituted in there. Bing, bang, boom. Then area will be substituted. So it will be substituted for 8, 10. Twice that will be printed as that. There we go. And that's how those substitutions will occur. Okay. Are there any questions? Because class is over. So if there are any questions, please let me know. Okay. Well, take her easy, folks. I'll see you next week.